Hello everyone, welcome back to another class of fundamentals of particle and fluid solid processing. We will continue our discussion on this fluid particle mechanics and particularly motion of particles in fluid. We have seen the problems related to terminal velocity, and now we will move on to another two interesting problems that will help you to understand that this CD versus RE curve that we mentioned and the two parameters CD RE square and the CD by RE. So, here there is a problem. It says that a sphere of known density falls freely under gravity in a fluid of known density and viscosity. If the terminal velocity of the sphere is 0.15 meter per second, then calculate its diameter. Apparently very simple problem. And the second part, it is asked that what would be the edge length of a cube of same material falling in the same fluid at the same terminal velocity. Okay. So, at first understand the problem. A sphere of known density is falling in a known fluid. Known fluid means the fluid density and viscosity is known. The terminal velocity of this particle is known. Okay. So, the question is what is the diameter of this particle, okay. So, which means if we think of the again Stokes law, the terminal velocity expression, we can see that there is a ut expression is there, okay. But the point here again, let me reiterate that this assumption of Stokes law, why the assumption should be valid, okay, because you do not know in which region this terminal velocity is attained. Okay. Now, you remember that CD versus RE plot. There at the first part or at the low Reynolds number, we had Stokes law region, then intermediate region, then Newton's law region, and then boundary layer separation region. So, this terminal velocity at which region? To do that, you remember the methodology that we mentioned. There were two parameters, that CD multiplied by REP square and CD by REP. These two quantity gave two constant values and independent of either terminal velocity or the particle diameter. So, here particle diameter has to be calculated for a given terminal velocity. Okay. So, the parameter that we have to calculate is CD by REP, because if you look at that expression, it shows that CD by REP gives an expression which is independent of the particle diameter. Okay. So, irrespective of the particle diameter, this CD by REP is basically a constant value. And what is that constant value? This value is 7.12 multiplied by 10 to the power minus 3. I hope you remember this expression. Okay. So, here this expression is independent of the particle diameter. Similarly, CD multiplied by REP was independent of terminal velocity. Okay. Since the point is here to calculate the particle diameter, we have to find a factor which is independent of this particle diameter. So, we do the numerical calculations here by replacing all the parameters, because all the values are known here. This is the particle, your particle density and the fluid density. Okay. This is the mu that is given here, G value, ut and the rho f square. Okay. So, this gives a value CD by REP of 7.12 multiplied by 10 to the power minus 3. So, what is to be done next is that we have to come up with the CD versus REP plot, or the standard drag curves are typically given. Okay. Now, how it look like? So, from that expression, the thing you can do that for REP, okay, 3-4 points of REP, you take 1, 10, 1000, 10,000 and you calculate CD. This will give you the CD versus REP graph or REP plot, which would look like this kind of a value, where this, remember, this expression that we have got is for a sphere, which means the sphericity is 1. Okay. So, here we see that standard drag curves will have these many lines, that this we have already discussed in the previous class, that with the changing sphericity this line shifts upward. Okay. As it goes away from 1, typically all the values are lesser than 1, then it shifts upward. Okay. And this CD versus REP, okay, if we plot this CD versus REP relation, okay, this would give you a straight line, okay, for with a slope of positive 1, and it intersects at a point that is our REP, and this line is that CD versus RE. Okay. So, but this is a schematic. Remember, this whole thing is not to the scale, but to show you that how the standard drag force curves will be there, and where how you have to draw this CD versus RE line. Okay. So, if we plot this CD versus RE, in this case we get this expression, which is a which have a positive slope and will intersect this sphericity 1 line at some point. Okay. At this point, so this is basically the REP that we are looking for, and it intersects, in this case we see that it will be in the range of 130 numerically. If that happens, if we take the value 130, okay, which is this value close to 130, and then we equate that with the expression of the Reynolds number, particle Reynolds number, we see that all the parameters are known except the diameter. This gives the value of x, that is 619 millimeter. Okay. So, this is how we get the diameter, okay, irrespective of knowing the flow region or the settling region, because here you can see that this terminal velocity is not definitely in the Stokes law region. So, if you had assumed that Stokes law region and had calculated the value of ut, the value of diameter from the expression of ut, that would lead to a wrong value. Okay. So, by this you can find out the accurate value of the diameter. So, the first part, the calculation was, or the question was, if the diameter is this one, what is its diameter, that we have find out, that it is 619 millimeter. Now, what would be the edge length of a cube of same material, which means the rho particle becomes same, the fluid remains same, and the terminal velocity remains same. Okay. So, if that happens, then this expression is always there, as it is irrespective of the size. Okay. So, this is the same expression will be there for various size of particle having same terminal velocity. Okay. Now, since it is now a cubic in nature, okay, it is a cube. So, sphericity is different. Okay. So, it will have to maintain its same terminal velocity as of the sphere in the same having same material and settling in same fluid, okay, it will have its different dimension, because from the graph you can now understand although the relation remains same, it intersects the sphericity of a cube that we have seen in earlier class is 0.806. So, which means the second line from the bottom will be used for this calculation now. So, now we can see the intersection is at a different value. So, this would be your particle Reynolds number in such case. So, the point is irrespective of the dimension or the diameter, equivalent diameter, let us say here since it is a cube. So, irrespective of size of the object, okay, if the material is same, it is same fluid, it is settling at a same terminal velocity, the CD versus REP, this CD by REP relation in this case remains identical. But this line intersects at different points of REP for different sphericity values. For this cubic particle or the cube shaped particle, it has a sphericity of 0.806. We see that this line roughly this intersects roughly at a point of 310. Again, this is not to the scale magnitude here, it is the schematic that is shown. If we plot it in a log plot and do this calculation, we do this plot accurately, we will see that it is indeed at this 310 this intersection happens for sphericity of 0.806. If that is the case, we get the volume equivalent diameter of a sphere. Okay. So, this value is the equivalent spherical object, fine, having a sphericity of 0.806, that is settling in the same rate. So, for this diameter spherical particle, the equivalent sphere volume is this value. Okay. So, if this is the equivalent volume of that sphere or the equivalent sphere volume as that of the cubic particle, one side length of this cube particle will be 1/3 the cubic root of this value, which is 1.18 millimeter. I hope this is clear that how we have calculated this cube, the side length of a cube. So, what we did, since this is the same material, same fluid, it is settling at the same terminal velocity, CD by REP, this expression remains same. The drag, it intersects the drag curve of having different sphericity values at different points of REP. We initially find out that what is the sphericity of the object that we are calculating. In this case, it is cubic particle or the cube shaped particle. So, it has a sphericity of 0.806. So, this CD versus REP line in this case intersects this 0.806 at 310, which is here, and then we equate that with the REP expression. Now, these REP expressions are valid for the equivalent sphere diameter. Okay. So, it can be said in this way that a sphere having 1.48 millimeter diameter having sphericity of 0.806, which is basically the sphericity of cube, okay, is settling in the same rate. Okay. Now, we can find out what is the volume of that spherical object having sphericity 806, which we say that the equivalent sphere volume, and since this is the same volume of the cube, okay, we can find out its side length. Okay. With this, we move on to the next problem. Okay. So, in this problem, now we have a different scenario. The scenario is we have a particle of known size, density, sphericity, falls freely under gravity in a fluid of known density and viscosity. The question is, what is the terminal velocity reached by the particle? So, in the previous problem, we solved for a given terminal velocity, what is the size. In this case, we are now solving that what is the terminal velocity when all the other parameters are known except the falling region, the freely falling region. In this case, that is also unknown. Okay. So, again, instead of arbitrarily assuming that the Stokes law applies here or Stokes law region applies here, which may not be true. Okay. The strategy here again, we have to find out an expression that is known already, that CD by REP square. This value is independent of the terminal velocity. Okay. So, that method we will apply it here again, that is the CD versus REP square will have this expression. If we remember again that 4/3 rho F stands for the fluid, and thus this subscript P stands for the particle, mu is the viscosity of the fluid, G is the gravitational constant. So, CD REP square, this expression is again a independent and the dimensionless value that is constant for all the particles, okay, having this this terminal velocity, the size of this value that is mentioned here with sphericity 0.6, if the fluid remains same and the particle density remains same. Okay. So, what we do, what we will be doing here is, again we will look at the standard drag force curve and we plot this CD versus REP relation here. This will give a slope of a straight line that is having a slope of -2, because CD REP square is constant value. The CD versus REP relation, again from this expression, for different values of REP, if we put it like 10, 100, 1000, we get the CD values. Okay. Now, this CD versus REP, okay, this, as I said, now will create a slope of -2, which intersects this CD versus REP curve for different sphericity at different REP values. Okay. So, here we can see that since the sphericity is 0.6 here is mentioned already for this particle, it intersects this third drag curve from the bottom at a value of 40, near about 40. Again, this graph is not to the scale, okay, and with this line is also not having to the scale of -2, but if we plot it in log scale, we will see, and if we plot this straight line with a slope of -2, we will have this intersection, and this value will definitely be numerically equals to 40. Okay. So, now this REP 40 is known from this third line intersection to this REP. Okay. So, this REP is 40 here, which is nothing but this, again this expression is rho f x v, which is the volume equivalent diameter, okay, and ut, which is the terminal velocity divided by the viscosity. We solve this one for ut because x v is known here. Okay. Remember, here there is no place for the sphericity. Here the x v is directly this value 0.5 millimeter, because this REP already is having this sphericity into account. Okay. So, that is why x v directly of that value that is there, and we find that x t the ut, the terminal velocity is 1 meter per second. So, this is how we calculate the terminal velocity when the diameter is given, and in this case the diameter was given with a sphericity value. Okay. So, these two problems basically will help you to realize the importance of these two parameters, that is CD by REP and CD REP square. These two constant terms, when one value is unknown and one value is known. So, in that case we see that this expression, this CD versus REP and CD multiplied by REP square, when it is plotted on the standard drag curve plot, which are typically will be given to you for these calculations, we see that the CD versus REP will create a slope of positive 1, okay, which is independent of the particle diameter, and CD versus REP square, this CD multiplied by REP square, this quantity is independent of the terminal velocity. Okay. So, remember this summary, that for unknown particle diameter, okay, we have to find a quantity which is independent of this particle diameter, which is CD by REP, and CD REP square when the terminal velocity is unknown. Okay. So, this helps us to have the estimate of either the diameter or the terminal velocity, irrespective of knowing that in which region the particle is settling. Okay. Is it in the Stokes or the Newton's law region? We need not require to know this part, because here you can see that in this problem it is settling in the intermediate region, okay, which means there is no particular expression was there or the correlations, although that are available in the literature, but it is hardly difficult, it is very difficult to find out those expressions and to use it to the precise manner. Fine. So, with this I will stop here for today's lecture. That what we have covered today is that we have solved couple of problems that helps us to understand the utility of the terminal velocity, the utility of the two important parameters CD REP square and CD by REP. In one case the terminal velocity was given, we had to calculate the particle diameter without knowing its settling region, and in second case without knowing the settling region, we knew the particle diameter, we had to calculate the terminal velocity. So, with this summary I will stop here and we will see you in the next class with some other materials. Thank you for your attention.